Okay, so in this video we're going to look at the law of cosines. This is one of the tools, along with the law of sines, that allows us to get information about triangles which are not right triangles. So triangles like this one, that don't have a right angle in them. If we have a right triangle, we can use the Pythagorean theorem, but suppose we're given like a couple sides at an angle, or a side and two angles or something, of a triangle which is not a right triangle, can we figure out the rest of them? That's one of the things that the law of cosines allows us to do. And I also want to mention that this doesn't quite go away when you get to university. It's one of the things that people forget about, and it's not going to be everywhere in university math. But it does actually pop up, particularly in linear algebra courses in first year, and it's a really basic thing, so it's good to know. We're going to go through the proof, partly because it'll help you remember it. Proving things not only allows you to develop your problem-solving skills, but also it's a great way to help you remember it. Even if you don't make it all the way through the proof, you're never going to forget the problem statement after trying to prove it for 5, 10, 20 minutes. But also because I want to demonstrate an important concept in proofs involving or problem solving involving triangles, which is that you can draw right angles into triangles and circles and other things where there aren't any. Drawing right angle triangles into things is a really important, really powerful problem solving technique, because all of a sudden it allows you to use the Pythagorean theorem, and that's what we're going to do here. So without further blathering, let's get to it. What does the law of cosines say? The law of cosines says that for any triangle, and I've labeled the sides here, as you can see. I've labeled this side capital B and the opposite side little b, and then this side is, this side is capital C, this side is little c, and then we have here capital A and little a. And I should probably actually do maybe an orange, because this is going to be kind of hard to see. There we go. Capital A and little a. So that's the correspondence between the sides. The little lowercase letters are for the angles, and the corresponding capital letters are the side across from there. And so I'm gonna pick one of these at random. It doesn't matter which one I choose, and you'll see what I mean in just a second. I'm gonna pick C and say, all right, C squared is equal to A squared plus B squared minus 2A times B times cosine of little c, where little c, of course, is the angle across from C, from big C. So the angle in between the sides A and B. And this is why it's called the law of cosines, of course, because of this cosine popping up here. But I just wanted to emphasize that there's nothing special about the C here. I could equally say A squared is equal to B squared plus C squared minus 2BC cosine of little a, or B squared is equal to A squared plus C squared minus 2AC times cosine of little b. Right? As long as the thing that we're taking the cosine of is opposite the thing that is being squared and equal to everything else, we're good. So it totally doesn't matter. We'll prove it for the first one, because they're all the same proof. It's totally arbitrary. We can say without loss of generality if we want to be formal about it. Although you don't have to worry about what that means, unless you're taking a pure math course and doing proofs, which I hope everyone does. But I want to, just before we begin, note that this involves squares, right? We're not saying anything about C. We're saying something about C squared and A squared and B squared. I mentioned we're going to draw a right angle and use the Pythagorean theorem. Squaring stuff in math really, really, really helps a lot of the time. When you start getting into vectors and doing linear algebra, you're going to notice that it's easier to work with the square of the norm of a vector, or a difference of vectors, than it is to work with the vector itself. All of this is kind of coming from the Pythagorean theorem. Squaring stuff allows you to use things like the Pythagorean theorem, and also then the law of cosines. Okay. So how are we going to prove this? I'm going to copy this triangle and bring it. I'm going to duplicate it rather. I don't want to copy the stuff behind it. I'm going to bring it down and let's prove the first one down here. And like I said, the way that I'm going to do this is, first I'm going to get rid of this highlighting because it's a little bit distracting. The way that I'm going to do this is by drawing a right triangle into this thing, and actually, so that I don't have to spin it around and confuse everybody. I think maybe I'm gonna totally renege on what I just said and prove and prove this one instead. I'd have to reorient the triangle, which I think would be a little bit disorienting if we wanted to prove it for C. So let's prove it for this one. Like I said, it's totally arbitrary which one we pick. So what I'm going to do is make and I can always do this with every triangle, and with a bunch of other stuff as well. I can always make a right angle here. I can connect this vertex of the triangle to the opposite side at a right angle. Drop down this perpendicular line here, and all of a sudden this opens up a world of possibilities. I now can use the Pythagorean theorem here. And I'm going to, as I do this, first of all, I'm going to label this side. Whenever you draw something into a diagram, you want to label it so you can work with it. I'm going to label it, call it, actually, I don't want to use H because H is for hypotenuse and it is not the hypotenuse. I'm going to call this D. We got A, B, C, D. That's pretty natural. So I'm going to label this side D. And I really want to stress the process in this because it can be a little bit sort of confusing where to start with proofs. I want to think what I'm aiming for, right? I need to find an expression for a squared. So I'm going to want to be squaring a. I'm going to want to be applying the Pythagorean theorem over here. But I also want a cosine of little a. That's something else that I need. So I'm going to need to be computing the cosine of this side, and that's going to involve this d. Well, actually, the sine is going to involve the d. The square of a is going to involve, the square of a is going to involve the d. The cosine of a is going to involve, and this brings me to the next point. This side here, I'm going to call this C1, and I'm going to call this C2. So, and we couldn't proceed with the proof if we didn't do this. Let me pick better colors for this. C2 is the side on the left here after I bisect this thing, or I'm not cutting it into equal pieces. After I break it into two pieces by dropping down this perpendicular line, I'm going to get 2 bits, and I need to label them so that I can use them. This one I'm going to call C1, and this one I'm going to call C2. And I want to be really, really careful about labeling everything and keeping it organized, because we're going to have a lot of letters floating around here, and it's really easy to sort of get confused and forget what you're aiming for. So I want to be really, really organized about this. So I'm going to start, because I'm trying to prove something about a squared, I'm going to begin, a very good place to begin is by saying a squared is, using the Pythagorean theorem, it is d squared plus c2 squared, the sum of the squares of the other two sides. And now my goal becomes showing that d squared plus c2 squared is actually equal to all of this stuff over there, right? That's what my challenge is now. And the way I'm going to do this is by using the D, which I'll put in purple, the D as my link to this side of the triangle, right? I need to think my way through this problem. I need to get a cosine of A in there. That is on this side of the triangle. I need to get a B in there. That is on this side of the triangle. I need to get a C in there. C, I need to keep in mind, is equal to C1 plus C2. So, and this is going to be an important thing to remember. I'm going to need to use this, I'm pretty sure, at some point in the proof. But the whole idea is that I need to get from this side of the triangle, from this side here, over into this bit. Start talking about the B's and the cosine of the A. And my link for doing that is the D. So let me start. If I don't know what to do, let me just start taking some trig ratios from the other side of the triangle and see what I can get. See what D is going to be equal to. And let me also see what cosine of A is going to be equal to. We put a bullet point here. What is cosine of A? I need a cosine of A in here. Well, it is going to be C1 divided by, I can do that a little bit better, divided by B, the adjacent over the hypotenuse. That's just the definition of cosine. So I have my cosine of A in there. What else do I want? What else do I want to get in here? I need to get a B squared in here. I have my B. I also need to get a B squared. What is B squared equal to? B squared, using the Pythagorean theorem again, is d squared plus c1 squared. And let me start highlighting these things to draw a little bit of attention to them. I have my cosine of a, that's what this is, and then I have my b squared. Actually, let me do that in green. I think that'll stand out a bit more. I have my b squared. That's taken care of. I also have the b that I need to get in there, and I have the c. I have the c is equal to c1 plus c2. So now what I'm going to do is take the right side of this thing. I'm going to take this stuff and substitute in the values that I've come up with over here. Over here, I have the cosine of a in terms of the c and the b, the c1 and the b. I have the b squared in terms of the d squared, which allows me to link it to this thing over here. And then I have also the c1 squared, and I have my c. I have my c and my c squared, right? C is c1 plus c2. So let me make those substitutions and see if I can scramble them around and maybe reduce them to this, get them to be equal to d squared plus c2 squared, which I know is then equal to a squared. That's my strategy. So I'm thinking my way through this proof. I'm not just staring at it and saying, because this is the biggest problem that people run into when they start doing proofs, is they don't know where to start. I'm just looking at what I know. I'm gathering up the things that I know about this situation, about this triangle, the trig ratios, what is equal to what. I'm writing them down, I'm organizing them, and then seeing how do I want to use them. Proofs, especially fairly straightforward ones like these, actually prove themselves if you're just organized and keep track of everything. And you'll see what I mean in just a second. So all right, what is, and I'm sort of starting from the other side, so I'm going to put this little arrow here to sort of remind myself of that. What is b squared plus c squared minus 2bc times cosine of a? Well, b squared plus c squared minus 2bc times cosine of little a, making these substitutions, this is d squared plus c1 squared, and that's using the green thing that I have here. This is why color coding is so nice. It lets me keep track of this. I have d squared plus c1 squared, and what is the next thing? I need a c squared. So c squared is, well, c is c1 plus c2, and I want to get those in here, right? I have a c1 in my formula for cosine of a, I have a c2 in my formula for a squared, a c2 squared there, and a c1 squared in my formula for b squared. So I want to get that c1 and that c2 into this thing. What better way than writing c as c1 squared, or c1 rather, I'm going to square it in just a second, c1 plus c2, and then this is all squared, and then I'm subtracting 2 times b, which I think I can leave as b for right now. I don't think I need to do any. I think it's probably a good idea to leave b as it is, and then because I'm sort of looking ahead and seeing it's going to cancel with this b, I want to be transparent about that. Putting in the b and then the c, which is going to be, I think it's a good idea to write the c as c1 plus c2. That's the, and let me keep the color coding consistent here. This is c1 plus c2. That's c. This is b in purple. 2 is of course equal to 2. This is b squared, and then what's the color that I haven't used? Blue. This is c squared, which is c1 plus c2 squared. And the last thing is the cosine of a, which is of course c1 over b. I figured that out up there, and yes, I didn't use pink, so I can keep it in this same color for continuity above. Okay, great. So I've made those substitutions. I saw that I needed to link to the other side of the triangle to get into that side and get a cosine of a and a b and a c1 in there, and d allowed me to do that. D and the Pythagorean theorem allowed me to do that. So that's what I did, and now I immediately see that I can cancel stuff. Right? I can cancel out these. I'm going to do this maybe in red for canceling. I feel like that's a good canceling color. B. I can cancel these, and now hopefully get some cancellations going on with the rest of the stuff, right? I need to keep in mind, what am I aiming for? I want to be left with this d squared plus c squared, because that's equal to a squared. I started with the right side here at the beginning, and you can switch sides, right? As long as in the middle of a proof, you can change which side you're working from. As long as you do some transformations to both of them to make them equal. If you want to write a formal proof, you need to do it in a particular order. But just to convince ourselves that this is true, we can switch and start working down. And if I start out with the right side, which is this thing, and I end up with d squared plus c squared, I know that's equal to a squared, and then I'm done. So I need to keep in mind that's what I'm aiming for. So what don't I want to cancel? I don't want to cancel the d squared. I want to keep it. And what do I want to end up with as well? I want to end up with a c2 squared. A c2 squared is going to come out of this. After I square this sum, I'm going to have a c2 squared, and I don't want that to be canceled. I want that to be left over. And I'm hoping if I've done this right, everything else is going to cancel. And I'll be left with something which is equal to a squared. So let's do this very slowly and carefully, as with all of these things. There's nothing worse than making a computational mistake or forgetting to copy something and thinking, being stuck on this. I can't tell you how much of my life I've spent doing that. I just don't want to. C1 squared, this is d squared plus c1 squared, plus now, after I FOIL this out, I square this. Hopefully we know that the square of a sum is c1 squared plus 2c1 c2 plus c2 squared. Now let me move this over to make a little bit of room. And now I am subtracting from up here after the b's cancel 2 times I'm going to multiply that c1 and I'm going to distribute it in to the c1 plus c2 and get c1 squared plus c1 c2. So that and let me just it's not going to be the exact same colors, but just to sort of draw the eye to this stuff, I think it's a good idea to keep squaring. Let me actually, that's a good idea. I'm going to put in green the stuff that I want to cancel, or that I don't want to cancel, the stuff that I want to be left over, and then I'll put in pink the stuff that I want to eliminate, that I want to get canceled out at the end of this. So and to keep this organized, let me move this non-cancel-y stuff over, stuff I don't want to cancel, over here, separated from the rest, and I'll bracket that off. That's equal to this stuff, and then plus, now I get to copy the rest of it and distribute in that -2. This is, I have a c1 squared plus c1 squared, that's 2 times c1 squared, and then I have a 2 times c1 c2, and wouldn't you know, when I distribute in this -2, I'm left with a -2 c1 squared minus 2 c1 c2. And then we get one of the great experiences of math, which is being able to go and slash everything, and it just goes away. It's a lot more fun on a chalkboard, but still quite satisfying. Okay, so all we have left at the end, just as we hoped, is d2 squared plus c2 squared, which is equal to a squared, and then we can put our little square. This is actually what we write in math. I didn't just say that because I was talking about squares. We actually put our little square saying the proof is done. That's it. We've finished. Stop reading. So what have we done? We started with the right side of the equality, the thing that we had over here, and we did some transformations using the Pythagorean theorem over and over again in our trig identities, working our way backwards, looking ahead to what we need and working backwards from that, and doing some careful canceling and arithmetic, and we ended up with, or algebra rather, not arithmetic, these aren't numbers, ending up with a squared. So that proves that this thing here is equal to this thing there. And that's it for the proof. So we've established it, and maybe we can take just a second to enjoy that before we immediately move on to the question which you've probably been asking since the beginning of this video, which is, why do I really care about this? And I'm going to, of course, this allows us to fill in triangles, right? Let me come down a little bit. I'm just going to talk about this briefly because you can do a bunch of practice problems and hopefully, and we will do some. But it's really easy to look up a bunch of problems on this, and apply it over and over again. And that's how you really get it to sink in. A great way to do it is by proving it yourself. A lot of people don't want to do that though. So if you're not so inclined, just try to do as many practice problems as you can. But suppose I have a triangle with sides A and B filled in here, and then I have an angle theta. Can I solve this triangle? What if I want to find this other side? Well, and let me call this C. Suppose, but let me put in a different color, a color that indicates that I want to solve for this. Can I solve for C? Well, I know that C squared is going to be equal to, from the law of cosines, to A squared plus B squared minus 2 times A times B times cosine of theta. Well, and we're assuming, I'm just going to put these in green to really, really emphasize that I know what these are, and I don't know what these are. These are a bunch of known quantities. I know what theta is, I know what A and B are. So I can just take square roots of both sides. I can say C is equal to the square root of this stuff, A squared plus B squared minus 2AB times cosine of theta here. And that allows me to solve for C. And now that I have C, I can use the law of sines to find the other two angles, or I can do something else, which is use the law of cosines to solve for a missing angle. Right? Law of cosines also tells me that if I know all three sides of a triangle, right, I can find any angle in the triangle. So suppose I know A, let's make a little less ominous A maybe, there we go, A, B, C, and suppose I want to know, let's do again, purple is the question mark color, or so I apparently have decided. Suppose I want to find theta. What is theta? If I know A, B, and C. A, B, and C are known. What is theta? Well, again, law of cosines tells me C squared is equal to A squared plus B squared minus 2AB times cosine of theta. So I can say this is true if and only if C squared minus A squared minus B squared is equal to negative 2A times B times cosine of theta. Now I can divide both sides by, well, actually, I think it's probably a little bit less confusing if I multiply both sides by -1 first. So this is if and only if A squared plus B squared minus C squared is equal to 2 times A times B times cosine of theta. And this is if and only if now A squared plus B squared minus C squared over 2 times A times B is equal to cosine of theta. And now, if and only if, this is the part where I get to solve for theta. If and only if theta is equal to cosine inverse, or we could also write it as arc cos. I'll do both, depending on what they're doing in your course. Cosine inverse. A lot of people prefer arc cos because it makes it clear that it's not cosine to the -1 or secant. Cosine inverse of A squared plus B squared minus C squared over 2AB. That's an ugly B. There we go. 2AB, which is arc cosine of A squared plus B squared minus C squared over 2AB. And so this just shows I can find the angle, right? If I know all three sides of the triangle, I can find any angle. Once I have that angle, I can use all three sides. I can use law of cosines 3 times to find all the angles, or then once I have one, I can use law of sines twice. But either way, if I have 2 sides and an angle, or all 3 sides, I can completely solve the triangle. I can fill in all the missing information, and that is very nice. A thing that this will pop up in vectors courses, so do make a mental note of this. That there's a fairly important thing about finding the angle, not fairly, extremely important thing about finding the angle in between in between two vectors, and then being able to test for orthogonality, but that's getting a little bit ahead of ourselves, that uses this. So it's great. It's a terrific thing to know. That you will be expected to know it. It's a sort of basic math thing, just 1 degree of fundamentalness, sort of, well, a little bit more than 1 degree. Similarly fundamental. I can't bring myself to say it. It's nowhere near as important as the Pythagorean theorem, but it's a thing that you should know. It's a fundamental thing that you should know, and is extremely useful. And the last thing I just want to leave you with a little thing to think about, which is that what is the domain of arc cos of or just the arc cos function, or the cos inverse function, because we didn't really pay any attention to this. I just assumed I could take arc cos of this stuff. We have tons of videos on this, on inverse trig functions and their domains and ranges, and how to graph them and stuff like this, but how to construct them in the first place. When are they invertible? But if you want to think a little bit ahead, either go take a look at those videos, or think about this for yourself. If you know a little bit about the arc cos function, what kind of numbers, what kind of values can arc cos take in, and how do we know? Do we know? And if so, how do we know? Using maybe some stuff that we know about triangles and the relationships between the sides of triangles, how do we know that this quantity is going to be in the domain of arc cos? How do we know that arc cos is actually going to be defined there? And that is a great thing to think about, and I will leave you with that.